Hello, my name is Nick Jarvis, and today I'm going to be telling you how I was able to detect malaria in blood cells using convolutional neural networks. So, a bit of background on malaria. I'm sure you've heard of the disease before, but I just want to get this out of the way. Malaria is a disease caused from a parasite that infects common mosquitoes who in turn infect humans. It's a very serious worldwide disease, which is responsible for around 450 million deaths per year. It's a serious concern for many people around the world. One way of detecting malaria is to examine a drop of the patient's blood on a slide under a microscope, known as a blood smear. That's what the image on the right that you were looking at. Usually the blood will be stained to make the parasite more visible. The slide is inspected by a laboratorian, but the accuracy depends on the quality of the reagents used to stain the parasite, the microscope, and the experience of said laboratorian. The goal of this program is to remove the experience part from the variables and to create more consistent results. I decided to take on this project because I like working on real-world problems, and this seemed like the most clear instance of that, as detecting this successfully can literally save people's lives. So the data I used is from the U.S. National Library of Medicine. They have a malaria cell image data set that I found hosted on Kaggle. I was looking through the data sets on there, and this one caught my attention and seemed the most interesting. The data set contains 27,558 images, half of which are infected, the other half are healthy. So essentially the whole program, it's just going to take in an input image. That input image will be passed through the classifier, and then the classifier will spit out a true or false. Does this blood cell have the parasite inside of it? So when I first started working on this, I wanted to play around with the data and see what I would be working with. And so on the left here you can see a distribution of the size and aspect ratio of the images, where the width of the image is on the x-axis and the height of the image is on the y-axis. And these are grouped into 10 pixel increments. So where it says 10 on the y-axis, that's really 100, just to keep the graph more consistent. And you can see there is a fairly large grouping right around that 130 pixels by 130 pixels, but by no means is that a majority. The images are spread throughout there, so I had to transform, resize the images to make sure that they were all consistent. And then on the right here you can see two infected cells, and you can see how the parasite inside of them looks radically different between the two. So the network, however we solve it, has to be robust enough to be able to handle that. So I did a bit of research before starting work. I looked at the CDC's page for malaria, read about the disease there. I looked at other solutions on Kaggle. Those were very helpful. I looked at some scholarly articles. This one is a kind of meta study on how malaria detection has been done in the past, what has worked well, what is kind of state of the art. So the actual network structure, first we take the image and we transform it. So whatever that size was before that we saw in that table before, we convert it into a 64 by 64 image with 3 color channels. And then we convolve it and turn that into 64 output channels. So instead of just going from red, green, blue, it gets convolved 64 output channels, goes through the rectified linear unit. We do max pooling to reduce the amount of computation we need to do later down the line. Take the output of that and pass it through 3 linear filters, each of decreasing size, the first one going from 16,384 input nodes to 1024, then from 1024 down to 64, and then from 64 down to our 2 malaria or healthy outputs. The hyperparameters for this network, when training it, I used a batch size of 64, a learning rate of 0.002, and I used 25 epochs, however, stopped seeing improvements after around 10 epochs. The network would save itself every time it would score a new high on the validation set. So eventually I was able to get it down to a 0.130 minimum validation cross entropy loss, which was pretty good. It was comparable to some of the other results that I had read and some of the other results that I had seen. However, with such a small network, there's obviously lots of improvement to be made. So here you can see a table of the network predicting results from random images from the data set and displayed on this table. And out of this randomly selected 100 cells, it correctly guessed 98. So I felt like that was a pretty good result. And for future work, one of the networks that I read about as I was working on this was called ResNet 50. Just seemed to be state-of-the-art, and some people had used it for this problem specifically. I didn't want to just directly copy ResNet 50 and just have that be my whole project, but it did seem interesting, and definitely want to play around with it at some point. Also, adding more layers. Obviously, it's a pretty small network as it is 2 convolutional layers and 3 linear layers. And then as well, having more data just coming in would obviously make it would make the system more robust. More data is never a problem. So if we want to take a look at the network in action, I did this all on Kaggle. And so here, this is where we load in the best state for the network, and I'm just going to run this again, the part of the script that generates the 100 outputs, and we can see what another random 100 choices gets us. This time we got 96 correct, and here you can see all of the different images. You can now start to see kind of the variance in some of these cells, how different they can be. But yeah, that's how I was able to detect malaria inside of these cells, and I hope you enjoyed. Thank you.